In this video, we're going to look at some examples of finding your absolute and local maximum minimums from a graph. So let's look at each of these points. Let's look at A. A is included in our graph and it appears to be a maximum from all the points near it, but it's not the highest point on my entire graph. So we'd say A is a local maximum. Now B, on the other hand, appears to be the smallest value in that near it, but it's not the smallest value on my entire graph, so B is a local minimum. C, on the other hand, appears to be the highest point near it, so we call it a local maximum, or sometimes you'll see the word relative maximum. So local and relative are interchangeable. D appears to be neither a local min nor a max. R is a local minimum, but more exactly, it happens to be the smallest point on my entire graph. So instead of calling it a local minimum, we call R an absolute minimum. And then S is also the absolute highest point on my graph, so we call S our absolute maximum. Okay, let's look at this example 4. A is the absolute minimum value on this graph, so we say A is absolute minimum. B, you notice, has an open circle, so that means that value B is not included in the domain of this function, so therefore at point B, we have neither a local max nor a local min. C also, although from the right it is the largest value, but from the left it's the smallest value. So therefore C, we say, has neither a local max nor a local min. Part D is a local min. R is our highest point on our graph, so we call it our absolute maximum. And S is a local minimum value. In example 5.6, we're asked to use the graph to state the absolute and local maximum minimum values of a function. So let's start by finding the absolute maximum value. So looking at graph 5, this point appears to be our absolute maximum. So we would state in our answer the absolute maximum value of this function f of x is 5, and it occurs at the point 4 or 5. Next, we're going to find the absolute minimum value. So we're looking at graph and we find the very smallest about. Now first we would think it would be this point here, but because that's not included in our domain, we would say that this function has no absolute minimum value. Next, let's look at finding the local maximums on this graph. So here it looks like it could have been a highest point, but it's not included in its domain, so we don't include it. So our first local maximum value appears to be occurring at 4. So we would say local maximum value of 4 occurs at the point 6, 4. Now you might also think this open circle would be a possible local maximum, but again, that is not included because it's not in the domain. And we have functions from the left that are higher than it. So now let's finally look at the local minimums on this graph. Well, this endpoint at 0 is also a local minimum, so a local minimum value of 2 at the point 0, 2. We have another local minimum value of 2 at the point 2, 2. Next, this cusp here is a local minimum value of 3 at the point 5, 3. And then our last minimum value here is not included because there's no open circles, so that would be it. Now on example number 6, we again have no absolute maximum because that top point is not included in the domain, but we do have an absolute minimum value of 1 at the point 4, 1. Now let's look at some local maximum values. Our first local maximum value would be at this point here. So we'd say we have a local maximum value of 4 at the point 3, 4. I'm going to go ahead and label all these points so I can easily find our order pairs. Next, let's find the next local maximum value, which will be this point. So we have a local maximum value of 3 at the point 6, 3. Our last thing we want to look for is we want to look for local minimum values. So our first obvious local minimum value appears to be at this point here. So we have a local minimum value of 2 at the point 7, 2. Now let's go back to this dot at the 2, 2. That is also considered a local minimum value because it is in the domain of the function and it's the smallest value near with x is near it because all other values are up there at 3 or above 3. So we would consider we have a local minimum value of 2 at the point 2, 2. For our next example, the directions are to find critical numbers of the function. Now, you need to remember that in order to find critical numbers occur when the derivative equals 0 or when the derivative does not exist, as long as those x values you find when the derivative does not exist is in the domain of the original function. So first thing you're going to have to do is when you're given a problem like this, you need to find the derivative of the function. So for f of x, our derivative would be equal to 10x plus 4. Second step, set your derivative equal to 0. So we would get 0 is equal to 10x plus 4. Solving this for x, we have that x is equal to negative 2/5. So this negative 2/5 is a critical number of our function f of x. And then last but least, do not forever forget this. A lot of students will forget. You need to figure out where the derivative is equal, does not exist, if it is possible. Not all functions derivative does not exist. For example, this f of x is a polynomial. We know a polynomial always exists, and we know the derivative always exists. So therefore, we only have one critical value for this problem, and that is negative 2/5. All right, let's look at another example. We're going to find the critical numbers of g of y. So we start by doing our quotient rule in order to find our derivative, low d high minus high d low over low squared. Now I'm just going to use some algebra and I'm going to simplify this derivative down. We find that g prime of y is equal to negative y squared plus 2y all over y squared minus y plus 1 quantity squared. So remember, next step is you're going to set the derivative equal to 0. Now here's a nice trick about fractions. The only way a fraction equals 0 is if the numerator equals 0. So let's just set the top equal to 0. I'm going to factor out a GCF, set each of those factors equal to 0, and solve. So I have two critical values here at 0 and negative 2. Last thing I need to check is when the derivative does not exist. Well, with a fraction, the derivative does not exist when the denominator is equal to 0. So we're going to solve this equation, and you should quickly see, and you can solve this quadratic any way you want to. I'll use the quadratic formula to solve it this time. And as I'm working through this, I notice, uh-oh, I get a negative underneath my square root in my quadratic equation. Remember, that means that we have no real solutions. So therefore, I know that this function is always exists. So my only possible critical values are the 0 and the 2. I hope this video was helpful and to understand the concept that we've learned in this section.